general relativity, step by step. I've said about as much as anybody wants to know about the stress energy tensor, so I'm going to talk about something else. I'm going to talk about the comma goes to semicolon rule. And this is a very powerful way of thinking, and I'll use it over and over again. Just imagine I'm working in a nice Cartesian space here, and I have a nice local equation. So I'm working in a Cartesian space. I've got a local equation in terms of Cartesian vectors, or Cartesian tensors, I guess. Just as an example, let's try this. I've got x mu as a vector, and I say that di by di x nu equals 0. So basically this x thing here is a constant. Well, I would write that equation down as x mu comma nu equals 0 with a comma here. Now that's in Cartesian space. Now if I generalize this to a general space, it might be some weird h theta system like I used a few screencasts ago. It might have curvature, you might be near a black hole. But even so, my local equation, I will need a local equation to talk about this physical rule here, which I've identified as true in flat space with Cartesian tensors. And the way you do that is to write, instead of x mu comma nu, you put a semicolon nu and state that that's equal to 0. And that's the generalization of the equation on the left hand side. And that is di x mu by di x nu plus, see if I can get this right, x mu nu, what's the next letter? I think it's omicron. That's going to be confusing. I'll call it a pi. That's going to contract down there. There's a nu there. What's left? There's a mu there. So this is what I call the covariant derivative. Okay, so it's just a generalization of that. So the comma goes to semicolon rule is if you identify that equation there as being true in Cartesian systems, or in a Cartesian system, then in a general curvilinear system, we have the the semicolon rule holding as well. And this is a valid tensor equation. And as I'm writing it, it doesn't look very powerful. Well, of course it is. I mean, that's what the semicolon is. What the semicolon is, the covariant derivative. We've got all this trouble with the Christoffel symbols here. And the reason we do that is to introduce, is to compensate for our basis vectors not being constant. But it's quite powerful. Because if I then combine that with the equivalence principle, what does that say? We can have a black hole here, we can have two orbiting black holes, terrible, terrible things. We can have spaceships moving about, we can have all sorts of terrible things going on. And here's me, and I'm falling towards a black hole, there's all sorts of terrible things. But if I build an elevator around myself, equations to me, or physics to me, looks like it does anywhere else. It's flat space. I might be this elevator might be accelerating towards a black hole and all sorts of things might be going on, but inside my elevator I can't tell. So inside my elevator I'm perfectly at liberty to use commas in my differential forms. And I can work with those. And then somebody says, but that only works for him inside that elevator. To which I reply, well, in that case, take your equation and put a semicolon there instead. And here's the killer. Because of the equivalence principle and because of the definition of Christoffel symbols, this equation here is an adequate, or well, it's the only generalization of this one here. So what it allows us to do, what the comma goes to semicolon rule allows us to do, is to consider what happens inside my elevator in isolation from the rest of the universe, figure out what the physics is using ordinary calculus, figure out the physics, write it in terms of a comma, and then some awkward person comes along and says, well, actually, you're near a black hole and your space is curved and your coordinates are all shot to pieces. And you say, well, all right, bang, that's it, sorted. The comma goes to semicolon rule is the right way to think about the equivalence principle and the definition of Christoffel symbol together. Comma goes to semicolon rule. And all it is you write down your equation like that, and all you have to do to make it work for all of physics and all of space-time, except the singularity in the middle of a black hole, I guess, is do this. Watch. That's it. That's all you've got to do. Colon goes to semicolon. It's so simple and yet so powerful, and I'm going to use it over and over and over and over again. I'm going to start the preparation for the Einstein field equations in the next screencast, and we're going to use this comma goes to semicolon rule. All it is you write down an expression in Cartesian coordinates, which is easy to deal with because it's just high school calculus. And then you say, oh, but we've got some very complicated curvature and all sorts of terrible black holes. Bang, that's it, done, sorted, stop.